Hi everyone. This is a style of multi-step problem that I call Hess's law and calorimetry. Sometimes I like to say Hess uses a calorimeter. There's multi-steps. It's right in the name. We're going to start with Hess's law to find delta H. Then we're going to convert that enthalpy change, that delta H, into a molar enthalpy, and we're going to use a coefficient for the moles. We're going to use the balancing number of the chemical the question is asking us to focus on for the moles. Then we're going to take our answer for that molar enthalpy. We're going to use this H to do a calorimetry problem in the appropriate way. We're going to have to really pay attention to our units as we do that. Here we go. Let's calculate the mass of methane that must be burned to heat 500 milliliters of water from 40 degrees Celsius to 60 degrees Celsius. First thing is, this is a calorimetry style question. There's numbers, we don't have one of the numbers, but there's numbers about two different things. There's a mass of methane involved here, and there's some numbers that go along with the water. Remember, our sign that we have a calorimetry style question is we have numbers about two, or more actually, different chemicals. However, though, we're actually going to have to start with Hess's law. Okay? We're going to the question is asking us to focus on methane in the end, but in order to do Hess's law, we need the balanced chemical reaction. And here, methane is going to be burned. We're going to do the hydrocarbon combustion reaction for burning methane. Let's get to it. Methane is CH4. It's a gas. It's going to react with two oxygen gases to make a carbon dioxide gas and two water vapors. Again, watch out. It really does make a difference. Are we going to have liquid water or water vapor? Because for Hess's law, there's a different number for those two different phases of water. Now, Hess's law itself, delta H is the sum of the moles times the molar enthalpies of formation of the products, subtract the sum of the moles times the molar enthalpies of formation of the reactants. Here we go. The products first. We have one carbon dioxide. One carbon dioxide, the molar enthalpy of formation, we would look it up in the data booklet. It's negative 393.5 kilojoules per mole. We also have 2 moles of water vapor. We look up the water vapor value in the data booklet. It's negative 241.8, again, kilojoules per mole. There's the products first. Subtract the reactants. We have our 1 mole of methane. I'm not sure the methane value off the top of my head. I go to the data booklet, methane, negative 74.6. Negative 74.6, again, kilojoules per mole. We're going to add 2. Oxygen is an element. It doesn't have a molar enthalpy of formation, so a 0 in there. I've got lots of buttons to push for our first step, Hess's law. Let's go for it. Negative 393.5 plus 2 times negative 241.8 subtract negative 74.6. We get negative 802.5 kilojoules. That's the total amount of energy released for this chemical reaction. It's the delta H. Our next step is to take that delta H, the enthalpy change, and convert it into a molar enthalpy. We're going to use the balancing number for the chemical the question asks us to focus on. Here, the question is about methane. H equals delta H over N. We just found the delta H. Negative 802 0.5 kilojoules. We're going to divide by the coefficient. Here, it's just a 1. 1 mole. So that's negative 802.5 kilojoules per mole. That's not very interesting mathematically, dividing by 1. However, conceptually, theoretically, it's a big deal. We're changing delta H into H. What this number represents becomes something different, and the units also change, going from kilojoules to kilojoules per mole. It's not that uncommon for us to have to divide by 1. It's not that incredible mathematically, but as I just said, theoretically, conceptually, it's a big deal. So we dealt Hess's law to delta H to H. We got through that. We have our H right here, our molar enthalpy of combustion for methane. Now we're going to use that value to do calorimetry. Okay? Calorimetry, we have negative heat gained equals heat lost. What's gaining the energy here? These 500 milliliters of water had their temperature go up. It gained energy. The water gained energy. What lost the energy? This methane was burned. The water experienced a temperature change. Its temperature went up. We have negative mc delta T. The propane was burned. That's an enthalpy change. NH. Okay. We have the mass of the water. We're going to convert that volume into a mass. The specific heat capacity of water, likely you just have in your memory. We can find it in the data booklet. Our temperature change is here. Okay. This H is the molar enthalpy of combustion for the methane. It's our answer. The moles right here is the mass over the molar mass. We're going to actually have to solve for N and then convert it into the mass afterwards. Okay, so here we go. N is going to be negative mc delta T over H. Negative. Our mass of the water. This m's coming from the water side. We have 500 milliliters. That's 500 grams. The specific heat capacity of water is 4.19 joules per gram degree Celsius. And the temperature change here was from 40 to 60. That's 20 degrees Celsius. And we're dividing by our answer over here, negative 802.5 kilojoules per mole. Here, we're going to have to be careful. I said earlier, we're really going to have to watch our units, because if we look at what's happening here, we want this to give us the moles. But you can see here that in the numerator, the grams cancel, the degrees Celsius cancel. It leaves us joules in the numerator, but we have kilojoules in the denominator. So we have two choices. We can convert the numerator into kilojoules or the denominator into joules. I have more space in the denominator spot, so I'm going to write that I'm going to multiply by 1,000 joules per kilojoule. And then the kilojoules will cancel, and those joules will cancel, and I'm left with moles. It is significant that we watch our units. Okay? There are other options on how we can manage our units. However, I would encourage you all to work on the energy conversion. Okay, so now I'm typing. There's lots of buttons to push here. 500 times 4.19 times 20 divided by 802.5 times 1,000. Pretty small answer. 0.052211838. That is the moles. That's the moles. We still have one more step to go. We're going to convert those moles into the mass of methane. The mass is the moles times the molar mass. It's going to be our answer. The number of moles is this number here just sitting on my calculator screen, and we're going to multiply that by the molar mass of the methane. Here's the formula. CH4, 1 carbon, 4 hydrogens, that's 16.05 grams per mole. This number is still sitting on my calculator screen, 0.05, etc. I'm going to multiply by 16.05. And I have 0.838. It comes out 0.838. I wrote the whole thing down. It's my raw answer. I go back and look at the question. 500, 40.0, 60.0. All of the numbers given to me by the problem had 3 significant digits. Conveniently, my answer here already has 3 significant digits. So all I need to do to wrap this up is get the units in there. This is the mass in grams. This is a multi-step problem. I'd like to call it Hess's law meets calorimetry. There's a whole bunch of steps to it. Our first step is to write out the balanced chemical reaction. An extra nice question would straight up give us the reaction. And then we're going to do Hess's law. Really watch your signs for Hess's law. Watch your button pushing. We're going to convert the delta H that we found from Hess's law into a molar enthalpy. We're going to divide by a balancing number. It's not uncommon for us to have to divide by 1. Watch out if it's a 2 or a 3. Okay? And then we're going to do calorimetry. This one happened to be about the mass. We might be doing calorimetry if there was different information in the question to solve for the mass of the water, the temperature change, the initial or the final temperature, or this one, the mass of the substance that lost the heat. Okay? So we had to use our calorimetry calculation, but this question, because we wanted the mass, we had that one extra step to multiply by the molar mass. It's taking different pieces of information we've encountered throughout the unit and combining them in a really holistic way. And I hope that helps.